Welcome everyone to our today's webinar within our DYNAmore Express series. Today, Kambiz from CADLM will give a talk and explain us a little bit how to speed up simulations with ODYSSEE and LS-DYNA, and probably eventually this leading to real-time crash simulation. Kambiz, can you hear me?
Yes, can you hear me?
Yeah, I can hear you. So you can...
Let me just share my screen.
Yeah.
If you can tell me when you can.
Yeah, I can see it.
My screen.
Yeah, now we see your Outlook.
PowerPoint on.
Yeah.
Is this okay?
Yeah,
can you see it?
Yeah, we can see it. Perfect.
Okay, perfect. Let me go basically. Yeah. Okay, so good morning, everybody. Thank you very much for being there. We have the pleasure of collaborating for a few years now with DYNAmore. So last year we decided to extend this collaboration to a higher level, which means that our solution, which I will be presenting to you, is now also distributed by DYNAmore. Worldwide, actually, so in particular in Germany. So we are very pleased that we can actually push the usage of this very innovative solutions even further with our old friends from DYNAmore. So what I want to now, by the way, there is an announcement, I think, on DYNAmore or on CADLM website concerning this collaboration. If anybody is interested in announcements, they can go and have a look at. Now, the topic of my talk will be machine learning for ROM, for machine learning for reduced order modeling, or based on reduced order modeling for real-time optimization. So the objective is to do real-time simulations, but really we are talking about optimizations, and you will see why. But you will see that it actually applies to everything else. So we will see this. Now, our just one or two slides on ourselves. We are aiming at CADLM at transforming all the data you have at your disposal in order to extract knowledge from it, in particular to use it for accelerating product design, as I said, via real-time parametric simulations, whenever it is possible. Okay, so it's not always possible, but whenever it is possible, we want to do it. Now, we are traditionally or historically involved in data mining and machine learning before it actually became in fashion. CADLM is a company which exists since late 80s, actually. It's gone through many adventures, but since something like 10 years ago, we started working on AI, and at that time, they still were called expert systems, but then you know the story, it picked up so fast that now a lot of people are doing. So essentially, these are our know-how: AI, machine learning, model reduction, which I will say more about it because it's directly related to what we do with LS-DYNA. Optimization, reliability, and risk and robustness. Now we are we started selling our software actually because before 2019, actually beginning of 2019, we were just doing services, but we started to put it on market, and we are very pleased actually that in spite of the COVID year, within 2 years of availability, we have something like 40 OEMs, very encouraging for us, mainly in the domain of automotive, I would say, but also quite a few in aeronautics. So this is mainly where we are active today, but we also have now companies who are also exploring our solutions from other fields. Now, what do we do? Now, the essential work we are concerned with is creating predictive models. Of course, this is what engineering modeling or simulation is about. Now we know that, well, simulation creates historically a lot of data. Not all of it are used. More or less 10% of the data which we create are actually investigated, or even less. So we thought that, well, we should have a look at that. All the data, and not just one or two responses you're interested in, and try to find relations between those data. This can also be related directly to anything which comes from sensor measurements, that's physical measurements. So we think that by combining simulation data and physical data, we can actually arrive at a better quality predictive models. This has direct impact on the cost of everything we do today in simulation, and our domain of application is essentially real-time predictive modeling. It's image, sound, and sensor-based prediction, and of course fault prediction. You will see I will have a few examples of these later. So our software is positioned more or less in midway between these three technologies: simulation, system modeling, and machine learning. And of course, we exploit all three. From a marketing point of view, well, we are more or less placed where up here, where actually data becomes more available. So I would say it's also related to the complexity of the product. When it's no more easy to define a model by just a few assumptions and parameters, like most optimization software do. Well, we go and look into the data, all the data, and try to exploit this domain. I won't go into detail of that because time is short. I just say that we have a few packages, so we'll come back to this. Let's start here. Now, traditionally, what we do when we do optimization or any repetitive analysis is that we create a set of data. We analyze those data by what we call a solver. The output of that solver allows us to make a decision, and we are satisfied with the decision or not, and we continue. This is typically an optimization loop, and it involves the solution of a function. And that function for most applications is an LS-DYNA run, for example, for a lot of you. It's a solver. And this solver, when we decompose it, we can see that it has many blocks. It has a CAD modeling, it has a mesh modeling, it has a solver run, extracting the responses, post-processing, etc. So it's a complicated thing, and a lot of efforts have been made last 20 years for automation, which have simplified this, but still we think that, well, this gray block in the middle need not be done every time. So this is what we want to do with our solution software. We want to use this block as little as possible by relating directly the parameters to the end responses. So we want to relate this data to the decision directly. Now, when is this usable or useful? Well, whenever you have anything iterative, like trial and error, parametric studies, you have a model, you calculate it, but you want to repeat that, I would say in order of tens of runs. Or you want to do more, where you actually let the optimization engine to do the job for you. Model fitting is an example. You go up to hundreds of runs. When you want to do a robustness reliability, well, of course, this is again multiplied by another factor, so you're in the order of thousands of. So you see, all this is relatively costly, and a lot of times you just leave it. You just don't do it because of the cost, or you do it with a very simple methodology, very simple response surfaces, and well, when the result is there, it's not satisfactory. So what we think is that there is a way of doing this differently, in the sense that if we spend a little time and money at the beginning, which is an amount which is fixed, you will see, we can exploit that to build a model, which we call a real-time model or a reduced order model, which as the number of iteration goes up, actually that cost doesn't change. So this is a huge advantage, or it changes very little. Whereas if I wanted to do traditional direct iteration or even response surfaces, this goes up linearly. So in terms of what we can handle as model variables, well, we can handle also anything which is related to directly to the mesh or even topology of the system. They can all be design parameters. They could be represented in your mesh. They could be topology. They could be form or assemblies. Anything which represents a change in your model can be handled. Remember that at this point here, we said we want to avoid that. So anything which is here can be considered as a variable, whether it's inside the model or outside the model. So this is one thing. The second thing is that we know that, well, to create our model, we need some starting point, and the starting point for us is sorry, I'm a little bit no, this is okay. So the starting point is a DOE, is a typical design of experiment, because that constant cost, which I showed you here, is actually the cost of creating a set of runs. Now, these set runs are essentially less important in terms of numbers than what we do with response surfaces, because they are not defined by the response surface. It's not a requirement of the response surface. It's actually an inherent property of the model, which defines how many points we need. And you will see it can be very low. We can come back to this in question and answer. And I will show you some examples of how this works. Before showing you examples, since I still have time, let me just check. Yeah, I still have some 10 minutes probably to just, before going for the examples, to show you a little bit maths, a little bit of basics of what we want to do. I hope you are not bored, but I will be very short. I just want to introduce to you a few concepts. Now, I did this, I have to go to the end of my presentation because I put this here. So let's see. Let me come back. Okay, so sorry, it goes out a little bit out of the screen. I copied from another PowerPoint, so it's a little bit out of form. My apologies. Now, recall how we do regression, or the equation of a straight line. Well, from school times, I remember that you know, regression or straight line was defined by some simple relation. You calculate the slope, or you calculate the intercept, and then you have the equation of the line. But there's not a unique way of writing this equation of the line. Okay, and in particular, there is one which we called, or we call still, parametric form, and that has a very interesting property, in the sense that instead of writing an equation which relates x and y, we actually write x and y in terms of another parameter, which is the time. No, sorry, which is it's not the time, which is another parameter. Now, this is interesting because it does two things. One, it creates a simple form of equation representing both x and y in terms of t, and it also decouples x and y. There is no more dependence of y on x. It's an indirect dependence on t. So this means that you can actually take any line here as t and write your equation in terms of that line, and not necessarily the original coordinate system. Now, what does that bring? It brings the fact that actually by doing that, you can simplify your equation, and you can do that by a simple projection on any axis. We call this a projection. and it reduces the amount of data actually which you have to store. Whereas here I had to store all the blue points. Writing it in this parametric form allows me to store much less information. That's only a lot of points are just replaced by a couple of information on the properties of this line. Now, this is the principle of what we call decomposition or projection. So keep this in mind. But you also remember from modal analysis that we can transform a complex second-order differential equation here into a set of simple and linear equations, decoupled. In the sense, each one of those equations are decoupled. We call this modal analysis, which is much easier to solve. So this is the trick. It's easier to solve this equation because it's diagonal than this one, which is not diagonal. Now, once we do this, we can go back and reconstruct our solutions. We also know from it's like this here. We also know from optimization there are techniques which are similar. For example, techniques like conjugate gradients. Instead of solving the problem in the natural variable coordinate system, we calculate some clever direction, and we actually proceed in that direction because that direction has something which is richer than the x1 and x2. It has some combination of x1 and x2, so it's a faster convergence. And a lot of other application. I just give you a few examples there. Even finite element itself has this property that instead of handling complex geometries, we actually simplify them to simple geometries. Now, one last word, and then I will go back to my examples, is that let's assume we wanted to predict a response like this. Now, obviously, no response surface modeling would work. I mean, which type of response surface can properly predict this? Or either we have overfitting or underfitting or everything you want with polynomials or whichever shape of interpolant. And secondly, it is extremely complicated to construct an equation system which can just, yeah, concerned with this. I don't know why it keeps on coming. Yeah, so instead of doing this, it's much reasonable to decompose it. You know, if I have a response like this, complicated, let's say finding the response surface or the polynomial or whatever, which actually passes through these points, the blue one, well, we'll have the problem of overfitting, which you can see here with the red line. Whereas if I decompose it into modes, you can see that those shapes are much easier to fit in the sense that they become simple geometries. We have the same thing here. If I wanted to find a sort of equation here, you can see for this line, well, it will be extremely complex. So I cannot predict a proper model for it. But if I decompose it into modes, like FFT and so on, well, those are very simple modes. So this is essentially what we mean by model decomposition or reduced order. Now, let me just do one thing because I'm connected to my mobile phone, which keeps on complaining. Can you still hear me? Is this okay? I hope so.
Yes, we can.
So essentially what, yeah, okay, because, yeah, okay, so I'll carry on. Now, so essentially what we want to do is doing things like this. That means decomposing complex systems into simpler systems. For example, if I have a typical crash scenario, which is identified by a set of geometrical and temporal unknowns, well, I will decompose them into geometry and space, geometrical and spatial and temporal temporal domains, and we can do this by algebra, and typical algebra can do it, or we can use machine learning as well. But doing this simplifies the resolution of a partial differential equation and allows us to solve simpler sets of problems. So I will keep this here, go back to, I can come back if you have questions on the theory, but I don't want to bore you too much with the theory. Let me go to examples now, which allow us to also discuss other aspects. So recall, I said this is not, this is the basis of reduced order modeling, and it's not a RSM, it's not a response surface modeling, because the approximation we find is based on the system itself. It's not a property of a fitting function, it's a property of the system itself, and it comes naturally from the eigenmodes of the system. So because that's why I spoke about decomposing into modes, because in reality, what we do, we decompose any system, whether it's linear, nonlinear, etc. We decompose it into behavior modes, but we have spatial modes, as in linear model analysis, and we have temporal modes, which are a little bit different. So we have the same methodology. Now, once we do this, it becomes extremely interesting, because anything I want to do with predicting a response, like here, I'm predicting let's say the thorax response of this dummy here. Well, I can do this in real time. In real time, I mean really a fraction of a second or a second, depending on the size of the model. So if I have some initial information, it's a DOE design of experiments of how this model react, I can use those decomposition, etc. techniques in order to construct a model which is nearly analytical. Once I have that, well, I can use that analytical model and use that to do optimization instead of the model itself. Notice that this is not a response surface I'm using. I'm using actually a surrogate, a replacement of the full time-dependent version of the model. It's just a little bit approximated, here you can see, but it has all other properties of the system. I can use this for doing population studies, generating statistics, correlations, robustness, reliability, everything I want to do with the model itself, I can do it with this surrogate version of the model. I can do sensitivity analysis, and of course, like crash, I can even calculate the animations, whether they are nodal values or element values. We can calculate them exactly the same way we do it. And of course, many advantages follow. Real-time computing, independence, complete independence of software and physics. We can automate this process in a sense that it can have really zero intervention, manual intervention requirements. The CAE effort is reduced because the number of runs which we actually need to construct that DOE is extremely limited compared to a response surface, which it can explode exponentially. Here we are actually limited by the dominant eigenmodes of the system. And since those are not many in any physical system, you converge by, I don't know, 20 to 50. So we can also expect that by 2050, number of runs, even for large set of parameters or variables, 15, 20, we still get a very good information of the information. This thing is really getting on my nerves. I'm just afraid to disconnect my mobile because I'm not sure if it will have an influence. So we have to live with this little nuisance. Sorry for that. Now, what we obtain is very precise and complete in the sense that it actually provides everything a finite element solution can provide. it's not just fitting on a value and a scalar value, reducing the whole system to one scalar. No, we are not going to that extent of reduction. We just reduce it sufficiently to have sufficient nodal degrees of freedom to represent the problem properly. And of course, we can what's the word? We can use an embedded version, actually onboard version of this technology to couple with any onboard software. Now, a whole lot of applications. I won't have time to go over all of them. I will selectively pick a few, but you can see here I have put all the problems. Here we have at least 5, 6 physics which are represented. All these problems which you know, which you can see, can be handled by exactly the same, the optimization of all these problems, or even simulation, parametric studies is handled in exactly the same way, same software, same methodology, without any major difference. So let's start by a simple example, which also is the simplest way of coupling LS-DYNA to Quasar I wanted to show you. Let's assume I have here a box beam, and I want to know, I want to do optimization, let's say on the pink and blue part, but the yellow part, I don't want really to waste my time for it, or vice versa. I want to study this part, not the other. So we intend to extract the yellow part and make it a parametric part, but we don't want to compute it anymore. That means we want to replace that yellow part by what we call a reduced model, which has 0 computing time. So the computation time will be spent here and not on the yellow part. The trick is that we do some, here you can see it, some sampling points, those blue points on this yellow part alone. That allows us to extract the behavior of the yellow part. Okay, this is more or less simple. And by compressing those data, by fusion of those data by the techniques I just mentioned, decomposition, projection, etc., we can replace that yellow part. Here you can see, I can show it. This is the full model simulation. This is just we have replaced all that yellow part by one beam, and you can see the behavior is exactly the same, more or less. It's a little bit more smooth because, of course, there are no interventions from interference from the buckling of the yellow part. But here you can see that everything is working properly. So we can extend this idea even further and go to direct Quasar-LS-DYNA coupling inside the code. So while this one is non-intrusive, I would say you wouldn't touch the code. It's just via the .k or the key file and a couple of includes which you do your coupling. Here we want to do the coupling using a direct communication between Quasar and LS-DYNA. Now the communication is more or less simple. At the time we want to calculate the nodal forces, we just, instead of calculating the way we do using the shape functions, we just use Quasar as a black box, and Quasar actually replaces all the element computations you have. So it simplifies everything which you put in this box will be calculated by Quasar, and everything which remains in this flow will be calculated by LS-DYNA. Now there is a specific keyword for it now. I won't go into details of that, but this is how this coupling is defined. So you define what we call what goes into Quasar, and you define actually this intersection. That means which degrees of freedom are connected to both, okay, which are shared, which are the nodes which are shared by two. It's defined here, and then the rest is done. Now the outcome is very interesting. Here you can see if I have a full model here, for example, I want to do a roof crash, but I want to leave the rest of the vehicle inside a black box because I don't want to calculate it every time. Here you can see that I can just concentrate on here. I can define the intersections, very much like a cut methodology. I can define the intersections and just compute this part, but the rest of it will actually participate, but via a reduced model. Here you can see the comparison of the result, and you can see that we lose a little bit of time here, but this is this is an old example. We have worked a lot on it, but essentially it's because well, it's a big model. Yeah? So you still need to compute things, but it will be done from a DOE, by the way. Yeah, so it will be done from a parametric model of the vehicle. That means you can actually replace this part by different parts, whatever you want, and just connect it to the same vehicle and use the same time. So a few other examples which show the application in yet more general way. This is completely decoupled. This is the easiest way to do actually what we want to do. Here I have a rubber joint. We do 15 runs as a DOE, and then we just use that DOE directly. There is no coupling anymore. It's just the runs are done before. And here you can see we can predict for any new set of parameters in 1 second compared to 20 minutes, the response, nonlinear response of the joint, linear, loading, unloading, and so on. We can do this for loading case or material. It doesn't matter. As I said, the differential equation disappears from the picture. That's why it works for any physics, since we are actually handling data. Here we have 15 runs which are done in a DOE with changing the position, the bolt speed, and the angle of impact, with some cases having rupture, others don't. And here you can see that here we can now go and predict the behavior, including whether there's a rupture or not, any other impact, angle, position, speed on the composite plate without actually redoing the runs. These 15 runs are sufficient to completely decode, let's say, decode the differential equation. And here you can see superposed the Lunar and the LS-DYNA. Yeah, even the rupture point is exactly the time, and the value is very well stated. Sorry, this one. I think there's something. Yeah, this is just a bigger picture. This we can then go up and upscale actually. Do exactly the same thing for any structure or substructure. Here we have reduced a 6-hour simulation into a 1-second simulation. That means if I want to optimize anything, we have here in this model 4 parameters per layer. It's a 4-layer composite bumper, where actually the thickness is the parameter. If I needed to do an optimization which needs 100 runs, for example, well, 100 times 600, 6 hours is a lot, while 100 times 1 second, it's just 1 minute. And we can here you can see that the predictions are very well matching. This works also. This is LS-DYNA CFD actually. It works for CFD exactly the same way as it works for this is a vein, a blood vein actually modeled by Lunar and not by DYNAmore, but it is based on I think 8, if my memory is it's correct. It's based on 8 initial runs. Yes, it states here. So we go from 2.5 hours to 2 seconds, and this can be used, or was used in this case, for a stent design, where actually the model, we don't want to change it. So why should we recompute it in every variation of the stent? We only vary the stent, and then the response of the vane follows. Here you can see the oscillations, the heartbeat oscillations are very well modeled by this. This is the same thing as I showed you, so I won't go into detail. Let's just, let me show you this example, and then I will go back quickly, go to some CFD examples and some image processing examples, because time flies. I think I have 10 more minutes, or even less. So here I have a sled test here. Now the one on the left, I think, yes, this is an LS-DYNA original run, and the one on the right is a Lunar run of the same model with some parameter changes. You can see this runs in 2 seconds. This one runs in 1 hour, but this one has learned from this one. So I need to run my DOE of LS-DYNA to learn how this system works. Once I have done that, for anything which is design related, I can use this model and not that model. Here you see those are the thorax responses, the blue lines. If I want to do a new design, and I can get that new design, the red one, instantaneously. If I want to do an optimization, I define my target, for example, here, and then I get within 2 seconds the proper material settings to do it. I can extend this to a full car crash situation with exactly the same methodology. Here we are optimizing the front rail thicknesses subject to different velocities of impact. We do 17 runs, and from those 17 runs, here you can see I have selected 3 validation cases, these 3 points, which were not actually inside the DOE, the parameter setting. And here you can see how well the prediction is, case 1, case 2, case 3. And we can get the simulation, animation, stress, strain, everything you want in 1 second instead of 3 hours. So if I want to go and do optimization, well, the problem is not, I don't need to oversimplify the model by doing response surfaces, which actually the problem with response surfaces is that they concentrate on one criteria, and well, everything else may go wrong, but we don't look at that. Whereas here it's not the case, so everything is involved, and it just replaces the full simulation. This is a combined, it's a more complex case where the vehicle is run over, that's a battery case, run over an obstacle. So we want to do this this simulation, which is done with LS-DYNA. Then we want to combine it with some thermal analysis to see how that impact has affected the thermal properties. Here you can see that the whole process, I will be very quick, the whole process can be reduced to a fraction of a second once we have done, of course, once we have done this original run. So we are going down from something like, I should have number of runs here. In this simulation, we are going from 2-hour runs on 128 cores per run to something like 5 minutes on a laptop globally. And here we are in the same order of magnitude. Here you can see it, the cost going 1,200 per core, going down to 0.3. So a lot of potential for stamping. You can do this for more or less simulators. We can do this. I will skip this because my time is short. This is natural frequency with typical optimizers, which I don't want to name here. The best solution known on the market is 175 runs, and with this technique, 58 runs only. and within few seconds. So extremely powerful technique. Now I will show you also. I have 5 more minutes. I will show you also some similar cases which for which we actually don't use necessarily the model. We just use images of the model. These are images of some simplified bonnet design here, the underlying structure. We have 8 images where the blue part is a steel frame, and then we have some other frame which is softer, painted in green, and the red dot is the head impact, is the head itself, sorry, impacting. So we know that, we assume that we know the response of these cases. So we have done, in our case, we have done LS-DYNA runs of all these cases, these 8. Now, once that I know this, I can go and optimize and find the best combination or the response of any other layout without actually computing. Here you can see I can calculate the acceleration or the displacement for even cases which are completely different, very different from what I had in my database. I still get a good approximation, and I can even improve them and compare them here to LS-DYNA run. This one here, you can see how good our response fits the LS-DYNA run, which was calculated as the best and lightest solution within just 1.7% error of the LS-DYNA. This is for ALE. It's too complicated, so I will skip it. Sorry. I just want to show you a few CFD runs, and then we can probably stop here. Here I have a CFD NACA profile where we learn from some 8 runs, 8 computations, and then here you can see we can predict the flow field. These are predicted, the ones at the bottom, predicted by Lunar, Odyssey, and you can see that they are exactly the same as the ones which are at the top, which are actually computed by the CFD code. Here I will switch to this one is a multi-physics run where we have a CFD model combined to a nonlinear code. I won't name it because it's probably a competitive field. But the idea is that I have one parameter here and another parameter here. Now this parameter is related to the stiffness of mechanical properties. The other one is related to the inlet fluid speed, so it's CFD based. Now here you can see that how that system globally works. The membrane is here. I run that 8 times, and then I use that database for my optimization. Here you can see that after the optimization, which had a threshold value to respect, this is the prediction of Lunar after only 8 runs compared to a full finite element, which is exactly the same. Here I have, I think I can then probably stop after this one, just looking at my 45. Yeah, I'll do this one and then I'll stop. Here it's a more complex situation. We have a restaurant air conditioning situation to optimize. The idea is to know where should I put the air conditioning, which is actually a box you can move on this line. This is a restaurant ground floor. Here you can see those are the tables, and these are the positions you can actually put your air conditioner. So idea is, where do I put it to get the best, what they call air aging? That means the age of the air, how frequently the air is renewed. So we want to find that position. Now we only do 12 runs because every CFD run is really costly. So we do 6. I think it's 12. Yeah, because it's all those cases, or maybe my colleagues have only done half of it. I don't remember. So the idea is to find out where should I put that here along that axis. And here you can see that we can actually calculate based on those 6 or 12 runs, we can calculate the dynamic evolution of the air. This is simulated, calculated by Lunar. This is the CFD itself. This takes hours, of course, on multiple cores. This is instantaneous. And here you can see, once I have that, we have validated it for 2 cases, for example. 6 means displace, and 7 means displace, so A and B. So we have validated whether the prediction there is good. Here you can see that 7 is very, very close. We detect here that's actually the position of the cooler, of the air conditioner, which has been predicted. And this one is a little bit weaker, but still is satisfactory. Now, using this model now for optimization, we find very quickly that position as being the best. That is somewhere around here, somewhere between 4 and 5. So in this area. So this can be very, very useful. Also, we can analyze directly the images. This is tire shapes related to responses calculated via frequency analysis, FFT, of the sound spectrum. We can associate to each one of these sound spectrum and go and find the optimal sound spectrum or a required sound spectrum for a case which we did not measure, this red one. So here you can see, if we know this, we can calculate this and so on. So many examples like this. This is, I said CFD will be the last one, but I can't let go of these. Sorry, this is the impact of a wheel on a block of concrete with all the response curves. These are acceleration curves actually measured at the center. Here you can see. So we have 22 runs which are run, and then we associate this wheel to different shapes of the wheel. So here you can see that for the 22 cases we have different velocities of impact and the different number of spokes here, 6 different types. And here you can see how this is the last one, how precise we can actually predict the response of a case which we did not have, a velocity which have not impacted. And for any number of spokes, we cannot create intermediate number of spokes because it has no sense. So we have imposed the number of spokes to be one of these. So here you can see that the response is very good. Okay, so I can stop here, but see if we have any questions, and I have also other cases which I can show you. Thank you very much for the moment. I hope this leaves a little bit of time. Sorry, I'm a little bit long.
No problem, Kambiz. Thank you for the very interesting talk. So far, I don't see any questions in the chat, but I want to address some. Can you give, I mean, based on your current experience, can you give some ideas on the learning time or the reduction process? How much does it take, depending on the model type? Do you have any experience?
The process takes more or less, I would say more or less. Yeah, it depends, of course, on the volume of data. Mm-hmm. But for all these cases I have shown you, it has never taken more than 20-30 seconds.
Okay.
So it's extremely fast. It's not neural networks, the algorithms we use, because, of course, there are some people, especially for CFD, who propose today neural networks. They say that, for example, this case, if you want to do the learning with neural network, it takes 24 hours. Mm-hmm. Okay, this fluid field. Yeah. Whereas for us, it takes 30 seconds. Mm-hmm. And the reason is that we use that decomposition technique. Mm-hmm. That is why it's so fast. We don't solve exactly the original differential equation. We actually solve a decomposed version of it. And that is why we are very, very fast. So we are mixing machine learning and the decomposition technique, which makes it very fast.
Mm-hmm. Okay, now the questions are popping up. But maybe first I want to address another one. Can you also somehow estimate the accuracy of the output depending on the input, how many inputs you have, like how many?
Of course, that is typically what we do. Yeah. Mm-hmm. Lunar does this automatically for you. We measure the accuracy of the solution compared to, of course, this is a posteriori measurement. That means we do use the validation cases. I showed you this here. For example, the accuracy has first been measured on this M6 and M5. That means comparison between this field and this field, which we can use any metric to calculate. And once it is satisfactory, because we have many methods which should be or could be tested to find the right, here you can see that there's a sort of optimal parameter setting which has been calculated automatically. Once that is done, we go on and do the optimization. So we don't use, of course, a model which is not predictive enough for optimization. It has no sense. We can do that.
Okay, and so the first question is actually it's also my question. You mentioned different packages, and also I'm now a little bit confused. What packages is doing what? I mean, you mentioned Lunar, Quasar.
Yeah, that is our problem. That is our problem. Actually, ODYSSEE is the name. Is nothing. ODYSSEE is a brand. It includes. Let me go. So I think I have. This is a kind of problem we have to solve one day, but. Here I think, here I have the ODYSSEE package, which includes 3 software. Lunar is our user interface, if you want, but it's very much oriented to reduce order modeling and real-time optimization, that it does the whole thing I showed you. And then we have another solution software, which is called Quasar. And that is the learning engine. That is the machine learning engine. And Nova is an optimizer. So the combination of this reduced order modeling, machine learning techniques for decomposition and everything, and Nova actually makes the platform which we call ODYSSEE. But most customers know us now under the name Lunar, because it's simpler, yeah, because that's actually what they see on the screen. So we sell it under this name. So we will find one solution to this, but since we started with this, we carry on.
Okay,
I hope this is clear.
Yeah, no,
there are 3. It's not much. It's not much.
Yeah. Okay, thank you. Okay, let's say I want to have it now. I mean, we are also distributing it. What about examples, manuals? Do you have like a resources online where I can download?
Yes. The answer is yes. You mean for DYNAmore, or you mean for customers?
For customers, for anyone who wants to try it out.
For customers, it's your business. So you have access to everything, and you provide them everything. The manuals, examples. We participate to the trainings because it's a new start for DYNAmore. So I think throughout this year, we will do shared trainings, but our support is active as a second line, but you will be first line. So everything is available. Yes, we do have that.
Okay, so do you have also an online resource for downloading something?
Yes, everything is available. If you go, I can actually show it, how it's done. Very, very simple, classical. We have on our website, you just download I don't remember what our website is called anymore. See, if you go to our website, can you see my screen?
Yeah, we can see.
Yeah. So you have this download, which allows you to download when it works, to download everything here. You will receive from us or from you a username, a password. This is once you have the license, and then you can go on and download all the manuals, executables, everything.
Okay, that's good.
Not as of course optimal as you are, because we are much younger. but it's working. Yeah, everything.
That's all it's necessary. Right?
Don't compare us to your efficiency. We are working on it, but at the moment we can.
No, it's fine. It's not about how you get it. This
is how you get it. Actually.
Yeah. Okay.
You go here. You have your username. I even have my own. Let me see. Let me try my luck. Here I can't. Here, log in. Maybe I can. So everything is download. Yeah, I have. So here you have a description of everything which is available in terms of executables. Those are the executables, which I just mentioned, Quasar or Nova or Lunar, whichever one you want. So we have packages with different pricing, and then you have all the manuals and helps and quick helps and everything, and examples for LS-DYNA, for example. We have that full car crash I showed you, the sled test. There are a lot of examples, and if you that box beam. But if you need other examples, well, of course, we have a lot of them, and we can provide you.
Okay, so there's a question coming in, another one. You showed this example with the car roof, which was actually decoupled from the rest of the car. This was right? It was decoupled?
Yeah.
Yeah. Let's say you're going to modify the car roof dramatically, like completely, which would then affect probably also the change of the structure of the car or affect it in some way. Is there some way to predict the effect, or is there effect, or how you would deal with this?
Yeah, there are some customers, some OEMs who are now pushing this technique to the limits. So I have to, I can't tell you which one, but some of these guys are really doing something extraordinary these days with our software, which I never thought it was possible. Customers always come up with ideas which you never thought you could do yourself with your code. Now, they actually even changed the complete vehicle. So, for example, they gather information from a series of crash tests, and then they use different vehicles to construct one model of a generic vehicle, and they use that. So, in a sense, yes, it is possible to make large modifications to the roof. However, well, you know, you should be more or less aware that everything at that interface point is whatever happens at that interface point is the key issue. So you should not probably change too much around here, I would say, because that's your interface. You can change anything you want here. I would keep that section and this section the same. But apart from that, everything can be changed, and you can even change the complete vehicle, as I said, but you just have to put another vehicle instead of it, again with the same interface. So yes, it's made for that, to change one part or another as you wish, without redoing the whole computation.
Okay. Okay, so there's no more question, and it's right 10 o'clock, so we have a full hour now.
Oh, very good.
So I will close the session, and I will ask everyone to fill out an evaluation form to give us a feedback, what you think about the session. With that being said, thanks again, Kambiz, for the nice and interesting topic.
Thank you. You're welcome. So if you have questions, either you contact me or DYNAmore for details. Thank you very much for listening. Thank you.
Yeah. Thanks again, everyone. Bye-bye, and see you next time.
See you next time. Bye-bye.